Alright, this video is trying to apply the chain rule to parametric equations. Recall when we're defining parametric equations, x is in terms of t, y is in terms of t, but our goal is to be able to find dy dx, so we can find the equation of our tangent line. We're going to be using this chain rule. We can write dy dt equals dy dx times dx dt. So if you're not really sure about that right away, we can look at a simple example. Y of t equals cosine of t squared plus 1. At this point, we could just find that derivative straight up, but we could apply this chain rule, thinking of x equals t squared plus 1. So the equation becomes y equals cosine of x, and we can say dy dt equals dy dx, and then dx dt. Okay. So if we start with that equation, dy dt equals dy dx times dx dt. We can solve the equation for dy dx by just dividing both sides by dx dt, and we get this equation. Dy dx equals dy dt divided by dx dt. Or in other words, the derivative of y with respect to t, the change in y with respect to t, divided by the change in x with respect to t, or the derivative of x with respect to t. And you can think of these as reducing out, so we get change in y over change in x. We'll get to that a little more formally soon. All right, let's look at an example. Find the equation of the tangent line at the given value of t. X equals secant of t. And then y of t equals tangent of t, and we're going to do it at the point negative pi over 6. So the first thing we'll do is take dx dt, and that would be secant t tangent t. And then dy dt will equal secant squared t. So now we can say dy dx equals secant squared t divided by secant t tangent t. Let me extend that over. And we can simplify this. The secants reduce, so we have secant t over tangent t. Secant t is the same as 1 over cosine of t divided by sine over cosine, so we can flip that, and we have cosine over sine. So we get 1 over sine of t, and that is the same as cosecant of t. Now let's plug in our value. The way we'd write that is dy dx. We can't say something like y prime because that's not really clear here anyways. We have to evaluate it at t equals negative pi over 6. And if we're thinking dy dx, typically when you have y prime, it's evaluated at that x value, and we don't have that x value in this case. So now we're just going to plug it in and say the cosecant of negative pi over 6. So that puts us in the fourth quadrant. Cosine of pi over 6 is 1/2, so this will give us the reciprocal of that of 2, and it's negative since it's in the fourth quadrant. Now we're going to find the equation of our tangent line, but we need a point. So our point will be, let's come over here, and we can say point secant of negative pi over 6, comma, tangent of negative pi over 6. And then the secant of negative pi over 6 would be the reciprocal of cosine at pi over 6, so it would be 2 over root 3 in the fourth quadrant, that's positive. And tangent would be sine over cosine, so the 1/2 over the root 3 over 2, and that will give us 1 over root 3, but in the fourth quadrant, tangent is negative. And so we just put this together, and we can write our tan line is y plus, because y minus negative root 1 over root 3, so y plus 1 over root 3 equals negative 2 times the quantity of x minus 2 over root 3. You don't have to rationalize that. It's not a big deal. Sometimes we want to, sometimes we don't care. Now I typically am going to try to move this over, so I'll put or. Every once in a while I'd like you to do that, and it will prepare us for some stuff to come later in the year. So just move that 1 over root 3, so that'll be a negative there. So negative, and then 2, and the rest we just copy down. And that's it. Let's take a look at one more example. And we'll say here, now I did I like to do it like this one here, where I find dx dt, dy dt separately. But if you end up writing this, you could do dy dx equals dy dt divided by dx dt. So if you're going to do it like this, please show that. And we're going to apply the chain rule to this. So we'll have 3, the outside one. The inside part stays the same. We make it 1 less power times the 2. That derivative of the inside function. And then dx dt will be 2 times 1/2 to the t. And then we subtract 1, so we get negative 1/2, and then it'll be plus 0. And if we simplify this, we can have 6 2t minus 1 raised to the 2nd power. And then the 2's are going to reduce here. This is t to the negative 1/2, so that can pop up and say t to the positive 1/2. Now we need to plug it in. dy dx evaluated at t equals 1. And we're going to get 6 times 2 minus 1, so that would be 1 squared times 1, so it's just 6. Again, we need a point. So our point will be 2 times root 1 plus 5, and then 2 times 1 minus 1 quantity cubed. So we'll get 7, 1. And we just plug it in again. So we have y minus 1 equals the slope 6 times the quantity of x minus 7, or we can say 1 plus 6 times the quantity of x minus 7. And that's it for parametric. In class, I'll show you another example which is a little more challenging for us to think about. And we're done.